Okay, let's talk about roots other than square roots. So, like a cube root. So, we want to solve x cubed equals 27. Well, I happen to know that 3 times 3 times 3 equals 27. So, 27 cube root equals 3. So, we take the cube root. So first of all, we write, if it's not a square root, then we write whatever power it is here in this bracket here, right? So x to the cube of 8 is cube root of 8, which is 2. Okay. Notice that 2 cubed and 3 cubed, they're a pretty big difference apart. As we increase the powers, the gaps between where a natural number would be, cube or whatever, grows. So they get farther and farther apart. Big differences with big powers. Okay, so that's cube root. A lot of the stuff is the same as with square roots in the sense of, the product of 2 cube roots is still the product. The product. Cube root of a product is the product with the cube roots. You can't break up sums, all that good stuff. Now, let's say we want to solve x cubed equals 17. All right, so first thing is, of course, we can guess. Now here it's a little harder to get that sort of a great guess because cubes are very far apart. But, 17 is between 8 and 27. Goes from 9, add 9 to 8 to get to 17, and you add 10 to get to 27. So it's about halfway, slightly closer to the 2. So we'll go with, like, let's say 2.5, right? And we can just change our thing here. All right, so now we're trying to get to 17. We're guessing 2.5. That's 15.625. It's pretty reasonable. 2.6 gives us 17.5. And so that was like, if you think of half units, so 15.5 to 17 is three steps of size 0.5, and going from 17.5 down is 1 step. So we want to be close to 2.6, quarter close. So that's 2.75. Doesn't really matter how precise this, 2.575. There we go. 17.07. That's a little on the high side, so 2.573, still high. 57, well, let's just try that. That's low. And you can keep, so somewhere between 1 and 2. And you can keep on iterating like that. Let's say, in terms of computing it directly, I guess I would do 17 raised to the, so what are we doing? We're doing cube root. So here I would do 1 divided by 3. And there you go, 2.5712. So notice that doing a cube root is like raising the thing to the 1/3 power. That's what we mean by fraction in the denominator in a power, is you taking the root that way. All right. So x equals cube root of 17, which is equal to 17 raised to the 1/3 power. It's all good. I should also mention, if we wanted to do, like, what does 17 2/3 means? That means 17 1/3 squared, like so. So there you go. And 17 raised to the 2/3 directly, right? All fits in together. Awesome. So you got your guess methods. Now, there is also a formula for computing it very rapidly. The general form, so it's a lot like the square root thing, only now we have extra powers, so that complicates things a little bit. So g's are going to be our guess, right? And if we had the solution, and we'll do x cubed equals 17 here. So if you took 17 and divided it by g squared, that should equal g if g was correct. Right? So we're thinking of g as being the correct one. That's got the most weight. But it's not the correct one. And so it's okay, how might I correct it? Well, I know that g cubed equals 17. So g is equal to 17 over g squared. All right, if it was exact. It's not exact. So we can try to average that. You could just average it just like we did before. We'll try that. So g plus 17 over g squared. Or you can do, over 2. Or you can do a weighted average, which is basically, so there's 3 factors of this guess, right? What if we said 2 of them were the correct ones? So 2 times g, 2. Then we have the third one, which is the 17 divided by g squared. It's a good idea to minimize that anyway, because raising something to powers makes it less reliable. And then, so now there's sort of 3 things, and so we divide by 3. That happens to be, calculus says this is good. All right, so calculus, that's the formula that it comes up with for computing this thing. All right, so let's try that out. So we've got 2 proposed formulas. So the good one was what? So we had 2 times x plus, so this was 17 divided by x squared. That's always makes me sad that you got to use that power thing there, but okay. And then divide by was it 3? 3, because you got 3 things, right? All right, so that's that formula. And then we had the other guess, which is just an average. So it's the same setup, but we think that that could be cool. And divide by 2, right? So let's go take a look at our table. Oh man. All right, so you can tell already that, so our answer is 2.57128179. Is that right? So what's 2.571591. 5. Yeah, so we're almost there in terms of the guess. Maybe I'll just, so there we go, and then 2.57128. Actually, I think that does it for that one column. All right, so starting with a guess of 2.5, 2.573, 2.57128, and 159. And so that really goes very quickly. In terms of the more naive formula of weighting the two things equally, it gives you 2.61 and then 2.57. Well, and so all of these things are, you know, they'll eventually get there, but so like let's try their guess of 2.61, right? And then 2.5527, 2.580. I mean, it's getting closer and closer, that third column, this Y3, but it's taking a lot of time. So it really did matter in terms of how quickly this stuff converges, but you get the answer eventually. But yeah, so calculus wins. It doubles the precision every iteration. So if you were accurate to up to 2 decimal places, the next time you'd be accurate up to 4, and the next time 8, right? Just goes like crazy like that, which is why it's like you do 2 or 3 steps and you're done. Anyway, and again, so you have to figure out a good starting guess. Let me just, what happens if I did the same stupid thing before, 17? So that's a really bad guess. And, it's coming down, but it takes time, right? So you don't get really great precision until you get close. 7141, and then we're almost there, right? Yeah. Actually, the averaging formula seemed to do better farther away, and then it gets to be less good as you get closer, right? So that's, in some sense, a really bad guess might be compensated better by the average thing, but as you get to be a good guess, you'll want to go to that other formula. In any event, that's how you compute it. And in general, solving something like x to the n equals m, you would use the formula n minus 1 times g plus m divided by g to the n minus 1 divided by n. So it's like same reasoning before. You have n minus 1 factors of g dividing into your target to get the other version of the guess. You weight it with n minus 1 copies of itself in that new factor, and then you divide it by the n to get that average. All right? So if I wanted to do x to the 5th equals 132, then that means I would do 4, my guess, plus 132 divided by g to the 4th, all divided by 5, right? And so let's just clear everything out. What was it, 5th power? And I was trying to go for 132. So I plug in 4 times x, so that's my guess, and then 132 is the interesting bit in terms of this problem, and then you raise that to the 4th power, and then divide all of that by 5. And that's going to be my iteration algorithm. Now, just conceptually, fifth powers are pretty big, so like 2 to the 5th I think is 32. 3 to the 5th is like 240, so it'll be between 2 and 3, I guess. So let's try a table. Let's just try 2.5. So that's not too bad. 2.67. That's getting pretty close. 2.65530. So we're already 1, 2, 3, 4 steps in. We are at 131.99. Again, notice that I had a reasonable guess, right? It wasn't totally wacky. If it was wacky, it would take several more steps to get there. And then 2.66, oops, 65530.728. And that should do it for us. Yeah, so it was like, what, 3 or 4 steps? Cool. Let's say I had a bad guess. I just start with 132. Look at that. That's a really bad guess. I get 105.6. Try that. 84. Notice how it's kind of slow to get there. I mean, we are rapidly, well, not rapidly, but I mean, it takes some time. I'm just typing it in fast because we're nowhere near it. And now we're finally get it right. So when you guess far away, it's going to take a long time. So it's good to have somewhat of an idea. Of course, if you had an idea, you might not even need to do that, because who needs the 5th root of 132? Oops, sorry. 1 divided by 5, and there we go. So 2.65530.728. So that's the 5th root of 132. And that's pretty much how it goes. So that's how you actually compute all these roots. Why do I care about telling you this? I don't know. I think it's kind of neat. I don't want people to think calculators have some special powers that you can't get to. No, it's just this. I mean, they're probably doing something else. But fundamentally, this is what could be done. This is how people could compute it before. It's a very effective and quick method if you had to do it by hand, which I wouldn't recommend. It's a lot of multiplication and stuff and division and things, and take a while, but it's doable, right? And a lot of times you don't need to compute these things out for a couple of reasons. One, you might actually need the exact thing, because when you do further manipulations, those things might go away or come out to be some other convenient form or something or other. So you don't necessarily want to translate everything into decimals right away. Two, a lot of the times, even though maybe the 5th root of something is part of the solution, the underlying idea behind how we just did this, the calculus stuff that I didn't tell you why, how it works, it's a fancy form of this kind of guessing and checking on some lines. But it's for another time. But a lot of times that method itself is what we use instead, right? So you can just get the answer directly. You don't need to come up with the algebraic form, like with the square roots or the 5th roots or whatever kind of root stuff. One, that form may not even be accessible. A lot of times we just simply can't get it. But even if we can get it, a lot of times it's just better to not get it in the first place and just go directly for the approximation. Just solve the problem you actually care about. That's important to keep in mind, that that's an option. All right, so that's real numbers and roots. And now what remains is